morning. It's Friday. Time for a usual Coding Train live stream. If I seem a little bit subdued, it's because I'm a little bit worried about today. Today is the day that I'm once again this month of January. Where are we in January? A little past the middle. I'm dedicating this month of January to attempting to work through. I'm sorry, I'm looking at the chat. To work through building a simple neural network library from scratch in JavaScript. I spent some time working on some matrix math stuff, building a simple working through the feed forward algorithm, and today is the day to tackle a topic. One particular technique for training the neural network, for having the neural network learn, and that technique is called, it's not called quaternions, as you might suspect. Oh, wait. But it is something that does often cause me to run out of the room in fear, and it's called backpropagation. Now, a couple things I want to mention. Number one is, eventually, I will be replacing a lot of the internals of this library that I'm building with a more sophisticated engine that's been highly optimized to do matrix math and also has a lot of libraries, a lot of classes and objects and library functions for doing deep learning stuff called deeplearn.js. So that hopefully by the time we get into February, that's where my focus will lie in looking at some more sophisticated models of deep learning systems to kind of do fun and creative stuff in the browser. But I'm still, I want to use this time together in this live stream to kind of dive into the guts of how these systems work, see what happens if we can not worry about optimizing or efficiency and just kind of build the pieces and parts and put them together, get something to work so that we can start to understand how the algorithms work, have a language, a common language to speak to each other about the pieces of these algorithms so we can ask the right questions later when we start to do projects and other types of things. How's this sounding? Is this okay? So I have done something somewhat shocking, which is that I've prepared notes. And there's an S on that word note. Notes. The plural of note, meaning more than one note. And not just more than one note, or pages of notes. Page 1, page 2, page 3, page 4, page 5, and then even some printouts of some code that I wrote at one point earlier in my life with some mistakes in it. That's some of the code for the backpropagation algorithm. Oh, there's even yet another page on the pad that I didn't rip off, so another page of the notes. I don't know how much these notes are going to help me. I want to say that, once again, I should thank, and I'm going to do this multiple times today, but a lot of my knowledge has come from this book, Make Your Own Neural Network. You can check the Coding Train Amazon shop for a link to purchase this book and other books that I recommend or use in preparation for a lot of my videos. And so this has been extraordinarily helpful. I also want to mention, but I don't know where to put this. I'm going to need to refer to this. Let's put it over here. I also want to mention 3 Blue, 1 Brown. And I've been watching in particular, let me pull this up here. 3 Blue, 1 Brown. I have been watching the playlist. Let's go to playlists. Well, there's a couple here, but I've been watching this playlist on neural networks. And I talked a little bit about how I'm doing this fundraising and training for a half marathon. I actually I did my training run at the gym because the weather is terrible here in New York. I watched videos 3 and 4, chapter 3 and appendix chapter 3 like multiple times on a treadmill on a little iPhone. So it was probably not the most optimal way to experiencing these videos, especially when I felt like I wanted to pause. to like contemplate for a second, and then like, bouncing around. Fortunately, no one was harmed in the watching of said videos on a treadmill. But these videos are extraordinary. Even more so than this "What is a neural network?" Video. This gives you a really nice, intuitive understanding through diagrams and all sorts of stuff about the backpropagation algorithm. You will also, I would highly recommend, if you want to dig even deeper into this, the Essence of Linear Algebra series is perfect for a lot of the matrix math stuff. But in particular, this Essence of Calculus playlist. And in particular, I'm looking for something about the chain product rule. The chain and product rule, which are necessary for the backpropagation algorithm. So I'm really struggling as to what to do here, because there's no way that I am going to cover in depth what's here in 3 Blue 1 Brown's channel. There is probably no way that I'm going to cover with the same level of depth what's in the Make Your Own Neural Network book. And by the way, I should also mention, I was looking at some of this code yesterday. It looks extremely helpful, but I haven't had the chance to dive really deep into it. But, oh yeah, this too. This is a free online book by Michael Nielsen that looks like 3 Blue 1 Brown used as a reference. And if we could go to, how the backpropagation algorithm works. Oh boy, how about I just do a dramatic reading of this page instead of trying to do it myself. So this, I wish I had spent some more time with this page, because I think this would be extremely helpful. But I don't think that I'm going to go as in depth as any of this content today. Eat the notes. Did that work? Could I actually like feed them through my ear? So this is my plan. This is my thinking as of right now. Play a lot of scary music so that I don't appear too serious while I'm talking about backpropagation. This is my plan for spooky backpropagation. I am going to talk through how the algorithm works in generalities as it relates to this diagram that I went through in somewhat detail about the feed-forward algorithm. So what does it mean to suddenly have an error here, and then correct these weights, which are tied to the error, and then propagate backwards those errors to adjust these weights, and in a many more layered system, just keep propagating back and back and back and back. So I want to talk about that in generalities. Then I want to look at how the weights are, how the error is kind of like portioned out, and how that can be expressed with matrix math, because I'm going to need that from our library. And then I'm going to refer back to my videos on gradient descent and adjusting weights based on gradient descent, and the 3 Blue 1 Brown videos. Just present the formulas that are sort of at the end of those videos and implement those in code. So I don't think I'm going to derive all of the pieces of the backpropagation algorithm today or ever. So definitely, because I would like to, so I might like to return to that, like put in some filler videos. I do think that other people are better equipped to make that content than I am. So I'm going to try to stick to where hopefully I can be of most help, which is kind of figuring out how to implement the formulas in code rather than prove or derive them. But it's important to at least have a discussion of the understanding of those formulas. This is my thinking. I'm just kind of talking it through. And then I can hopefully do some coding challenges, because once I have the library built, I can say like, hey, let's train it on this. Let's do a coding challenge to use this library on this particular problem. So that'll be a slight difference in some of my coding challenges of the past, where there was sort of no code. Maybe there's a P5 library, of course, but where I'll build these quick machine learning examples using the library. And then if people want to refer back to how the library was built, they can do that. Okay, so that's my thinking. What does everybody think about this? I feel like I'm a newscaster now with my notes. Wait. Oh, that was all the spooky piano I have? I thought that was a much longer effect. Okay, so how are we all feeling about this? How are we feeling about this? Merin, how did I do today? Merin in the chat says, sounds like a solid plan. What could possibly go wrong? No, what could possibly go wrong? Me trying to explain. One thing I've actually learned, which is kind of interesting, and I might as well plug this while I'm here, is I'm participating in this conference put on by the Processing Foundation and the School for Poetic Computation. What can I maybe called? Let me if I do. I meant to type in SFPC, Learning to Teach. So I'm doing a short presentation at this conference. Is this it? No, that's from last year. Last year, yeah, 2018. So one thing that I'm discovering is when I make mistakes in code and have to figure out and debug them, that seems to be a useful technique for education. Meaning people watching are like, oh yeah, I make those mistakes. Oh, I'm seeing how you figure it out. Oh, this is helpful to me, or this is interesting, compelling, and I'm learning something. Whereas when I spend an hour trying to explain some math formula but have the formula wrong the whole time, that's not so helpful. So it's not like, oh yes, I'm seeing your process of how you get it wrong for a while, and then you realize that later and kind of have to do. So what I'm discovering is a lot of these sort of mathematical or algorithmic discussions, especially if they have like complex notation, require something called, I believe it's called preparation. Which I have here in the form of notes. What was I saying? So I'm trying that. But most likely, I have to admit, I wouldn't be surprised if I just end up redoing, I need a couple tries at this. So I probably should do those tries, not live streaming in front of a live audience on YouTube, but I don't, when else am I going to do it? So I got nothing else going on right now. So thank you for being guinea pigs. And this is actually what happened most recently. If I go to my channel and go to this particular video, this particular tutorial was made on Tuesday of this week. Though if you look at the live stream archives, there was a live stream from last Friday, a week ago today, when I went through this exact algorithm. But I made so many mistakes, it wasn't worth trying to edit that together in some way that made sense. It just made more sense to just do it again. So with this gradient descent stuff, I'm just kind of fair warning in advance. I'm kind of in my mind thinking of today as, let's just give this a try and see how it goes. Now the other thing I should mention is, Simon. Okay, I will. Simon is telling me that if I watch his live stream, I'll learn better how to pronounce Merin. Okay. Now, the other thing I should mention is I was going through all this and looking at it, and I kind of have the formulas and some code, I think, for all of the weight adjustments that I need to do. But of course, I kind of forgot about the bias part, so I haven't looked at that yet. So let's see if we could put the backpropagation formula stuff in for adjusting the weights. And then if any of you who know what you're doing more than me, which is probably a lot of you, maybe you can help me figure out how to put the bias stuff in. Okay. And in regards to the camera that goes to black, I will just mention, since people are talking about it in the chat, I'm going to fix that soon. You know, sometime in the next year is what the solution to that is to put this firmware on the cameras called Magic Lantern. So I just have to basically, like, you know, it's kind of like, should I start live streaming on time and have 2 hours, or should I try to fix this camera thing for an hour and only have an hour left? It's often the way it works out, so I'm not optimizing for fixing it, but I will. Okay. Now, as you know, on the coding train, especially when attempting things like backpropagation, it's always good to stay hydrated. Hello, Brazil. It's amazing that people in Brazil are watching. All right. Now, let me compile some resources here. It's already getting warm in this room. Okay, so I want this playlist available to me, and I want I guess I should verify. I guess I should get one of these check marks on my channel, huh? I also want this playlist, available to me. So this is, I want to reference neural networks, essence of calculus, neural networks and deep learning free book, and the Coding Train Amazon shop, which has this book here. Then, now my own videos. The ones that I think this relates to are this particular video. Hey, look! Somehow my subtitles are closed captioning are on, and they are on in German, it looks like. Who wrote these? I discovered recently that I can. Sometimes they don't show up. Sometimes it says who captioned the videos here. Sometimes it doesn't. Okay. Here would be another video from Suraj. Has a lot of videos about this topic as well that are terrific. Then I also want the perceptron. Which is basically you know, I think I talked about a bunch of stuff multiple times in these videos. Because isn't this kind of like a video about the feed-forward algorithm? That's interesting. Part 1. 15 minutes? I forgot about this. That's so interesting. What's in these videos? I think I made like duplicate content. Hold on.
Welcome back.
Let's just kind of scan through this real quick. Oh, I think this is me kind of like sketching out what I need. Oh, and then I stopped at the matrix where I need matrix math. Oh yeah, so I did do this kind of twice. There's the feed-forward algorithm in a previous video. That's so interesting. So, okay, that's fine. So what I'm looking for, though, is this one. And maybe somewhere in here. The training function is where I want to kind of pause for a second, because it's basically the same code. Where do I have a nice, if someone could find me a time code in this video where I have a nice screenshot of the train function. I guess I can actually just open up the code on my computer. Might be more efficient. Sorry, everybody. I'm just like trying to get organized here. Let's see here. Where's that Perceptron? Sketchbook. Is there anybody see Perceptron? Probably coding challenge. Well, maybe I should go to. Oh, I should really talk about the new website stuff too, but it's too many things. Coding challenges. Perceptron. Huh. Didn't I do it as a coding challenge? Why is it not numbered? That's a mistake. Hold on. What video is that? Oh, that's not a coding challenge. It's actually like a tutorial. Somehow it's here though, maybe? Let's see. Nope. Oh, this is different. Yeah, this is kind of relevant here. All right, so that I can reference if I need to. Okay, part one. I wonder why? Why? What's the? Someone give me the too long didn't read answer. Why? Why? It's 2 million views. Why? Why? All right. Whew. I really wish that the climate control system in this room could be fixed. It would really make things better for me. 11:30. Okay, so we got this, 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 we got this. Okay. And there's also like mathematics of gradient descent. By the way, just if I go click on videos, that's nuts. Something is wrong with the universe is if my video shows up first. That is really a problem because I expect a lot of these other ones are much better. But it probably has to do with the fact that I titled it that way, math. So if I just search for gradient descent mathematics. Yeah, okay, how about gradient descent algorithm? Just gradient descent. There we go. Okay, good, good. That's good. Oh, I'm down there. That's fine. I'm happy with that. Look at these other ones first. Okay, so so this is actually the video that's most relevant. All right. Oh, okay, Google knows it's me, and so they're putting my videos up there because I watch them a lot. That's probably so. But I'm not. Am I signed into Google? Hold on. They probably even know. They just know, even if it's an incognito window. I don't know. I don't know, Google. I don't know, Google. Google just knows still. The incognito window is like, they just know, right? All right. The delta rule. Oh, you should do a video on the delta rule, learning algorithm for single layer neural networks. I think I did that already, right though? Isn't that kind of like what my Perceptron video is, basically the delta rule? Just accept it, okay. Tushar in the chat saying, I have a question on the last video. Okay, let me take a couple questions. I'll do anything, to procrastinate from trying to talk about gradient descent in a video. So I'll take your question. Okay. Oh. Do you guys still hear like a weird, okay, hold on. Do you guys hear a weird like echo, like the timing of when you hear the sound that's being piped through the system versus the sound through my microphone is off? Like if I do this. Oh, shoot, I wasn't looking at the chat. I'm sure if that question was asked, I missed it. Which is a reason for me to maybe plug the Patreon for a second. I do have a Slack channel that it's a little bit easier to keep an eye on, and where a nice, friendly community of folks discuss different things that I'm doing in the videos and provide some financial support for the channel. So if you go to patreon.com/codingtrain, you'll get an invitation to the Slack channel. Okay. All right. There is no echo. All right. All right. All right. All right. We got to get this started with. Let's get rid of some. Let's catch up to where we are. Oh, whoops. Desktop. Let me get this going here. Localhost. There we go. This is where we last left off, with a feed-forward neural network that will give me a random output. Now we want to put the backpropagation algorithm into it. If I open up Atom, should have my code. Let me open up, this will be another useful reference that I should bring in here. And I think now I've got everything I want to talk about. Did I make the joke last time? Oh, I think I did. It wasn't very good. It wasn't very good, though. Sorry, one thing that I've also learned to do is sometimes I'm responding to stuff in the chat, but not saying what it is, which is very confusing if you're watching and you're not even seeing this chat, so I'll try to be better about that. Taran asks, why don't you prefer Visual Studio Code? Maybe I do. I'm just not as used to using it, and I keep meaning to set it up, but I kind of have all my settings and everything in Atom vaguely the way I like them. Although I really should turn off all the autocomplete stuff. Does anybody know how to do that? All right, I think I've got to get going. I think we've got to start this. Oh, I just got a notification that the coding train is live. Maybe I should go watch that. Sounds interesting. All right. Let's read some random numbers. This'll get me a little warmed up here. I'm getting too old for this YouTube thing. 46,737, 88,027, 35,497, 22,863, 65,011, 12,228, 66,430, 11,825, 835, 81,838, 94,431, 63,995, 91,171, 18,273, 47,730, 784, 39,208, 34,268, 18,093, 17,018. Thank you. Okay. One thing that I should probably do really quickly in case you need to make a website where I read any possible random number. I'll give you some footage for that real quick. I'm kind of working on this on my own anyway, but 0. Well, should I be looking at the camera? Probably should be looking at the camera. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 30, 40, 50, 60, 70, 80, 90, 100, 200, 300, 400, 500, 600, 700, 800, 900, 1,000. Yes, 1,000, 2,000, 3,000, 4,000, 5,000, 6,000, 7,000, 8,000, 9,000, 10,000. I think you could put together, though, the 1, 2, 3, 4, 5, 6, 7, 8, 9 and the word 1,000. 1,000. And you could put together 20,000. Yeah. 100,000. So I think you have enough, right? Because you've got 100, 100,000. No, but you need 110,000. 110. No, you need the and. 110,000. No, but these don't go up that high. They only go up to 99, 99. So you have a 99,135. Yeah, you're fine. I think you have enough. Right? You could probably make a bunch of video clips, have a random number you picked, and have me speak that random number, right? The and part means you want million. All right, fine. Million, billion, trillion. All right. Whatever I missed, I'll get you later. Am I being really quiet? I didn't want the volume to be peaking too much. Okay, glad that we worked that out. Oh, I need my notes for sure. Like, seriously, I'll do anything. I'll probably agree to do, that double pendulum simulation or something now. I'll agree to do just about anything to avoid this backpropagation algorithm. But we're going to do it now. All right. All right, Adam, I need to command the settings and click packages, search for autocomplete. I guess I could. So what do I want? Sometimes I like the autocomplete though. Which of these do I want to turn off? I don't know. Now I'm afraid to disable it. What if I've been using it all along and I didn't know that I've been using it? Well, we'll leave it. Now I know where to look for this. All right. Can anybody come up with any reason right now why I shouldn't get started on the backpropagation thing? Okay. Oh, yeah. Shoot. Nobody has a point. What do you need a point for, though? There's going to be continuity errors. Point. Maybe you just need the audio, though. Maybe you're just going to use the audio, which is fine. All right. I'll come back later. At the end, I will take your reading random numbers requests. The stippling challenge. I already didn't I? Oh, yeah, the stippling challenge, right. All right. All right, here we go. Just need the mouth. Okay, this camera's off. I should, yeah, I know. So many, I'll do the reading, I'll do that, I'll do some reading all the possible different numbers thing later. I'll configure it in a way that's better. Just hold on. Let's actually do some, let's try to get through this. So my goal right now is, let's see if I can get the backpropagation algorithm into the library by 12:30, which is like 45 minutes or so. And that gives me a half an hour / an hour to try to at least solve maybe XOR as a coding challenge. That's my goal for today. I need to like slow down here. I'm going to get to all this stuff eventually. I'm just doing my best. I got lots of videos. You can go back and watch those. My hair is really, really a mess today. I wore a nice shirt for all of you. I thought that might make the whole like backpropagation gradient descent thing a little bit less weird. Make it look like I know what I'm doing. All right. Clean. My glasses are very dirty. I'm really like, I just don't want to start. I'm going to start. Okay. Okay, here we are. This video, what I'm going to do in this video is, and I'm quite terrified at this moment, I should say, but I'm going to start to talk about what it means to examine the output. We fed in some input, we did the feed-forward algorithm, we got some output. I want to now look at that output, and I want to say, what do I think about that output really? Is it good output? Is it bad output? Is it right on? Is it a little bit off? And I'm going to, this is a technique known as supervised learning. I, the teacher, am now going to say this output is incorrect. Please adjust all your settings to make this output more correct. And I have done this before. I have done this in a video about linear regression and gradient descent. I have done this in a video where I made a simple perceptron, where I did this same type of learning algorithm. In fact, I've done this in genetic algorithm examples where I'm not using the same exact technique, but a different technique to sort of teach a system to do something. So this is what I want to do. You can think of all of these weights that are inside the network as these little knobs, little settings, and I just want to like always adjust the settings. And so there's going to be key terms that are going to come up here, like error. What's the difference between the output and the known correct answer? That's the error. The cost, well, over a large training data set, what's the sort of cumulative error of all, that's the sort of cost, the current cost of the neural network. And then this term that's called backpropagation. So if the error is the thing that tells me how to tune these weights, the error is right here. It's going to tell me how to tune these weights. How do I tune these weights? They're not connected to the error. They're connected to the thing that's connected to the error. So I need to propagate backwards. Feed forward is the process of moving all the data forward through the network. Backpropagation is the process of taking the error and basically like feeding backwards the error through the network. Now here's where I have to admit something. This is probably, I would say, I'm trying to think of a topic that I've tackled in any of my videos that's like harder than this. I can't think of one. I don't know that I fully have a deep understanding of this. I have implemented it before. I have spent a lot of time. I even prepared some notes. I prepared some notes for the first time in my life, which are right here, that I'm going to use while I start to explain this. But it's kind of unrealistic, and I'm probably not the best person to go into all of the math. So what I'm going to attempt to do is give a kind of just general overview of how the algorithm works, look at how pieces of it actually work, the math of it, in particular as it relates to matrices, because I'm going to need that understanding to implement it in code. And then I'm going to present some of the formulas to you that are the formulas for how you change the weights based on the error, and then try to implement those formulas in code. I'm sorry. I put in a, I guess it should probably be edited out, but maybe it should just stay in. But I put in a order to try to fix the temperature in this room, and I'm worried that someone's going to just enter the room and try to fix the thermostat. So I thought I heard like keys jiggling. I got worried. So anyway, okay. So this is my plan. So probably take 2 or 3 videos. But so my goal is really the implementation. And I'm going to provide to you a bunch of resources if you want to dive deeper into the math. Let me just mention those to you. So number 1, Make Your Own Neural Network by Tariq Rashid. This is a book that I was reading on the subway this morning. You can actually get it on your Kindle app for a very inexpensive amount. You can also find it here on a lot of books that I recommend on my Coding Train, Amazon.com/shop/codingtrain. The 3 blue, 1 brown video series, What is a Neural Network? What is backpropagation really doing? Backpropagation calculus. You could pause right now and go watch these videos, which will give you a much deeper set of knowledge about the math that I'm going to use, as well as this, the essence of calculus, right? One of the things that's used in the math is the chain rule and the product rule. So this particular video might be useful to you, as well as this particular online book, which I found through the 3 blue, 1 brown videos, Neural Networks and Deep Learning. And I'd be remiss if I didn't also mention Suraj's YouTube channel that I've mentioned a lot on this video. Has a lot of different, a lot of my videos, a lot of different videos on similar content, especially if you're interested in Python and using the TensorFlow library and that kind of stuff. Okay, so that's that. Now let me start. I think we're ready to start. Time out for a second. Just looking at the chat. All right, so that was my brief little introduction. And the next thing I'm going to do is I need to do some erasing. So let's take a, oh, I always do this. No, I definitely, no applause is, I just want to have a freeze frame of this whiteboard because I'm probably going to erase it. What do I want to keep? I think in the end, I think I just want to erase this. I think I'm going to erase this and start over. Okay. So if you talk amongst yourselves, I'm going to erase the whiteboard. This is just water, in case you're wondering. Helps it erase a little faster. This is whiteboard paint. So the whiteboard is actually painted onto the wall, which is kind of wonderful, but there's a bit of a problem. Number one is it's very glary. So it's very hard for me to figure out how to light this room properly because there's a lot of glare on the whiteboard. And then also it's very hard to clean. It's just, you can see here, can you see how dirty it is? Nothing would make me happier in life than to have a perfectly pristine whiteboard that's totally clean. But this is a start. So if I need to refer back to that notation, I will. All right. Okay. Let me check our various chats as they're going. And all right. I don't see anything like any emergency messages. All right. Oh, let me get my notes. Where do I put my notes? I don't have a place for notes. I need like a little podium for notes. Let me just look at them for a second here. Okay, this is where I'm starting. Okay. Got it. All right. I've erased the whiteboard, and I am now ready to start talking about the backpropagation algorithm. So let's assume right now that this is my output neuron. And just for the sake of simplicity at this moment, let's just pretend this is one of the hidden neurons. But let's just pretend that there's just one of them. So there is some weight. There's also a bias, but I'm going to come back to the bias at the very end. So I'm going to kind of do everything without the bias and then come back to the bias. There's some weight which is connecting this hidden neuron to the output neuron. Now, the input the output of this neuron multiplied by the weight is sent through here, passed through the activation function, and we get some sort of answer. Let's say that the answer that we get is 0.7. So that can be referred to as the guess, the output, but I'm going to call it the guess. Am I staying on the whiteboard? I'm dangerously close. I erased just pause for a second here. Let me put a little mark up here. So really output is the very top. All right. 0.7 is the guess. Now, in the I wrote it too high again. One more time. Wait. I'm seeing crazy stuff in the chat. No, all right, that's fine. That's nonsense that doesn't have anything to do with me. Sometimes I think if the chat is being blasted with emojis, it's like to get my attention, but now I'm only going to assume that's ever the case if it's the Slack channel. 0.7 is the guess. Now, in the case of supervised learning, where I have a prepared data set, where I have sort of like known answers, so I'm going to train the network to have these weights so that later on I can put in unknown data to get good results, I would have some sort of answer. And that answer could... This is terrible. If this is all that goes wrong today, though, I'm going to be really happy. I'm going to have some sort of answer. I'm really like pushing the boundary. I don't know why. I should just lower everything a little bit. Sorry, Mathieu, I'm making this like annoying to edit for like no reason. I would have some sort of answer, known answer. So I'm going to write that here. And I'm going to say the known answer is 1. I wanted this neuron, with this particular input that came in, I wanted to see the answer of 1. So this means now I also have an error. And the error is calculated with a simple formula. What is the desired output, the answer, minus the guess? What's the difference between those two things? So we can see is that the error is 0.3. So in my simple perceptron and in other videos that I've made, I've then taken this error and used it as a way to basically nudge that weight. I wanted a 1, I only got 0.7. I can make the weight a little bit higher to get more stuff, right? I want more stuff, right? I want that weight higher. Maybe the bias needs to be adjusted, but with 0.7, I just need to increase that weight. I need to increase the weight in the direction of the error. That's how this works. Now, here's the next piece of this. Let's say, however, that instead of just one weight coming in here, I have 2 weights because there are 2 hidden neurons, H1 and H2. Now we have a problem. We have this error, which I know I need to nudge weight 1 and weight 2, but which one's really kind of responsible for the error? There's a lot of blame placing going on here. Normally I would think like, let's try not to blame anybody, but this is the problem. And I could just say like, I don't know, take half of the error, increase them both the same amount. But there's a key aspect of the way that the learning process works with gradient descent and backpropagation is we really need to figure out who's responsible for the error. So let me take the scenario, these weights could actually be weights, where this weight is 0.2 and this weight is 0.1. Well, we could now make the argument that this connection is more responsible for the error because it has a higher weight. In fact, it's 2/3 responsible, right? This weight is double of this weight. So in fact, when we do these nudges, we take this error to nudge this one, but we'll nudge it only by 33%. And then we'll take this error, and I know this is going to go out of your view, but it's coming all the way back here, And we'll nudge that by, let's see, can you see this here? 67%. Actually, I should just do it back here, 67%. So this is a key aspect of and this, I've basically done this before. So this is where we look for this delta weight. We adjust the weight based on that error and the inputs passing through. Okay. So now, let me just pause for a second. How's this going? I'm getting good tips on how to fix my whiteboard issue. Oh, this camera went off, so I might as well fix that while I'm here. All right, no one's saying anything like is horribly wrong, so I'm going to keep going. Let me check my notes. What was the next thing? So step 3 is, okay. Step 3 is adding the layer here. Okay. But so maybe this makes sense to you, and if it does, good. Here's the tricky aspect. This is why this video is ostensibly about backpropagation. This is not the diagram of the neural network that I created in the previous videos. In fact, this hidden layer is connected to the inputs. And all of those have weights. And I spent a lot of time worrying about the indices. Let's get those indices correct. So this, if this is input 1, and this is input 2, I usually call those x. And this, by the way, the output we can refer to as y. It's usually what's often referred to as y. So if this is input 1, x1, input 2, x2, this weight is the weight from 1 to 1. This weight is the weight from 1 to 2. Now that might look backwards to you. It's the weight from 1 to 2, or it's connected between hidden 2 and hidden 1. But the reason why I'm numbering it that way is it's going to be in the second row of our matrix. This weight is the second row of our matrix. And this is a weight from 2 to 1, so I write 1, 2. And this is a weight from 2 to 2, so I write 2, 2. So here's the thing. If this error, which is happening right here, is used to tune these two weights proportionally based on their weights, well, how do I connect this error back to these weights? How do they get tuned? Well, what I need, one thing to realize is this is like a little section of what could possibly be a much larger neural network, right? There could be many more layers this way and many more layers that way. So these weights are just tuned based on whatever this neuron's error is. Right here it's at the end, so I can actually calculate the error directly. But here they're not connected directly to this error. Here they're not connected, they're connected to these. So what is the error coming out of here? If I just had that, if I had like hidden, E for error hidden 1, what does that equal? If I knew what this was, right? If I knew the error coming out of here, error hidden 1, then I could adjust these weights. Because the error coming out of here adjusts these weights, this error adjusts these weights. And this error, E2, error hidden 2, if I knew what that is, then I could adjust the weights coming into that. So this is the idea of backpropagation. There's an error here. It goes to here. Now I know if I could calculate these errors, then I could continue to go back here. And then if there were more, I would just calculate these errors and keep going this way. So this is the real question. How do I calculate that hidden error? How do I calculate the error of a neuron anywhere within the network that's not necessarily directly connected to the output, where that error is just a simple target minus outguess? I'm going to pause for a second. Okay. I think this is all still making sense. I'm going to look at my notes. I'm now finished with my first page of notes. Thank you very much. Maybe I'm not going to need a second try. I'll never need that page of notes again. I look forward to the time where I've forgotten how all this works again, because it's like years later, but I have this nice video that explains it, and I can go back and watch it. All right. Okay. All right. Okay. So the way that I want to do this, yeah. Okay. All right, I'm thinking about this. Sorry, oh, E1. Okay, yeah. All right. Okay. All right, I'm gonna, to figure this out, I'm gonna pull just a section of this diagram out over here. I'm gonna need to progressively over time make this diagram more and more complicated, but right now I'm gonna simplify for a second again. So what I wanna do is I just wanna take, actually it's sort of here already, but I just wanna pull it over here. So this is the output, and these are the two hiddens. This is the weight of, this is the weight of 0.2, and this is the weight of 0.1, and the error here is equal to 0.3. So what I want to, and this is the hidden layer. Remember, what I'm trying to, H1 and H2. What I'm trying to calculate is the error of hidden 1 and the error of hidden 2. Okay, so the way that I do that is by taking this error and getting a portion of it. What portion should I get? And I sort of said this already. 2/3 and 1/3. So if this is weight 1 and this is weight 2, right? This is a very simple scenario. This is almost like back to that perceptron again. Then what I want to do is say the error of hidden 1 is weight 1 divided by weight 1 plus weight 2 times the error of the output, E output. The error of hidden 1 is a portion of that output's error. The error of hidden 2 is weight 2 divided by weight 1 plus weight 2 times that output error again. We sort of said this already. I realize now but this is fine. It doesn't hurt to sort of do this twice. So these would actually be the errors here. These are now the errors, and I can just use the same gradient descent algorithm to tune these weights. But this actually is kind of a rare circumstance where everything's just connected to one thing. So what I want to do now is I'm going to make this diagram a little bit more complex. And I'm going to take the case of having more than one output neuron. And see how this works. I'm going to add another, so let's say there's 2 outputs, which means there's error 1 and error 2, right? Maybe this is trying to recognize a true, or we could actually recognize like true or false, or something, recognize a 0 or a 1. So in that case, maybe the desired answer is, is 1 and 0, but we got 0.7 and 0.3 as the outputs. So here, this error, I made this 2, let's make this 0.4. This error would be negative 0.4, right? And now, what I need to do is have more connections here. And once again, this is for this matrix, I've got kind of the same notation, 1, 1, 2, 1, 1, 2, 2, 2. Okay. Now look at this. Now, error 1 is one thing. What's the error coming out of hidden error 1? Sorry, hidden error 1. Is based, okay, pause for a second. I got it in my head, but I'm just going to Take a break. Shouldn't the error be squared? Yes. Yeah, when I get to the, yes. Right now I'm not worrying about that. It was asked in the chat, shouldn't the error be squared? When I calculate the sort of cost, the total cost, we're going to square, yes, you do square the error, but in this case I'm just trying to look at how this gets divided up. So if this is our diagram now, with two outputs, so there are two errors, known errors that we can calculate in our supervised learning system, we need to still figure out hidden error 1 and hidden error 2. Well, this still stands, right? This is still a part of the error coming out of here. It's the part that it's responsible for, it's how much is it responsible for 0.3. And so in that case, this should be error output 1. And I'm actually just going to, if it's an error on the output, I'm just going to say E1. So this is, and this now is this weight. This weight's a portion, and this weight's portion, right? Whoa, sorry. Oh, shoot. I literally trying to click undo. In my head, I was just like, undo. Let me look at my notes here. I want to make sure I'm being consistent about my 1, 1, and 1, 2. Yeah, I am. That's what I've been using. 1, 1, and 1, 2. Right. Okay. Yeah. Okay. Sorry. Let me do this again. This error coming out of hidden neuron 1 is the same as it was before. It's still the portion of the error based on this weight and this weight. How much are we contributing to that 0.3 error? Well, this one has a certain percentage and this one has a certain percentage. And that is weight 1, 1 divided by 1, 1 plus 1, 2 times that error. Now, here's the thing. That's just how much it's contributing to error 1. How much is it contributing to error 2? We've got to calculate that as well. And that is the portion of these two. And let me make sure I have a lot of space. So how much of weight 2-1 divided by weight 2-1 plus weight 2-2 times error 2? So if they're multiple, this is the total cumulative error of hidden neuron 1. It's portion of the connection from it to error 1 summed with all the other connections to error 1, and the portion of its connection to error 2 summed with all of the connections to error 2. And I'm kind of, it's not connected to error 2, it's connected to the output, but the output is producing that error. So this is its sum, right? Now I could do the same thing for this error. It's its portion that it contributes to this error, which is now weight 1, 2. Right? You can see that these are the same, right? This is its portion, that's where it's connected. This is its portion, that's where it's connected, right? It's percentage portion of the total weights, all connected to output 1. And then, how's it connected to output 2? Weight 2, 2. Its portion of the total of error 2. Of the error for output 2. So this is now how those errors are computed. So again, if the mathematics of gradient descent tells us how to take an error to nudge weights, then we calculated this error. Now we calculate the errors coming out of the output. These are our formulas for calculating the errors coming out of the hidden. And those errors are the things that can then, with gradient descent, tell us how to nudge these weights. Then if we had more layers, we could calculate these errors and keep going back. That is backpropagation. That is how the hidden errors are calculated. So this is the end of this sort of part 1 of just sort of like the basic idea of backpropagation. I'm going to check to see if there are any questions, which I will answer at the beginning of the next video. I'm going to check to see if there are any questions, or corrections, which I will mention at the beginning of the next video, where I will also implement at least just this much in the code. All right. All right, I'm not seeing any thing that I got horribly wrong. I actually think that might be fine. I did prepare, but the more we get through today, the less preparation I have. That's the problem. I was preparing, but then I kind of ran out of time. I gave myself an hour this morning to prepare from reading how backpropagation is, and I did watch those videos yesterday from 3 Below and Brown, but it's kind of, I went to sleep. Everything, I lie this way while I sleep, and all the knowledge, it just leaks out. If you look at the pillow in the morning, there's all these math symbols there. It's amazing if I could just put that back in. So what I want to do, I forgot actually, there was more to this. What I meant to do is actually, I meant to turn this into matrix math. But that's fine, I'll do that in the next video. Okay, this is going great. I never heard such feedback before. Amazing. Okay. Just wait to the part where I get here's a formula. Forget it. Let's just implement it. Okay. All right. So. All right. Oh. All right. Okay, I'm going to keep going. All right, so in the previous video, I went over how to calculate the error in a supervised learning system, right? The error is just the known answer minus the system's guess. Then what I did is talk about, well, how can I take that error and move it backwards through the system, feed backwards. Instead of feeding the data forward to the network, feed the error backwards. And the way that I can do that is by looking at, well, how much did each of these contribute to that error? Let's kind of make this error a portion of that error. And these were the formulas that I went through, right? Look at this neuron, hidden neuron, is connected to this output. This is the weight. How much is this weight a percentage of all the other neurons that are connected? It's just 2 in this case, so it's just the sum of these 2, but there could be many more. So what I want to do in the code now is actually add this training function where I send in input data to the network with a known answer and have the training function calculate the error. So calculate this. Basically, I want to calculate this vector, E1, E2. And I said vector, but this matrix, 1-column matrix. That's what I want to calculate. That's going to be a really easy part. So let's do that first. All right, so actually, in a previous video, I sort of set up this function, I think, right? This is the feed forward function where I just take the inputs and I feed them forwards and return the output. Here is a function where I take the inputs and get an answer. Now, ultimately, I should just be able to use the feed forward function, right? I might have to tweak this, but on the one hand, I should just be able to say, let output equal this dot feed forward inputs. No reason why I should be able to do that. And then, now what I need to do is calculate the error. So the error is error equals the target. So answer, maybe I should call this target. Targets, I'll call it target, it might be plural, right? These are the target output that I want. Targets minus outputs. So let's call this outputs. Again, the first example that I'm going to build is going to have just one output, but I want the system to work for as many outputs as there are. So in theory, I should be able to say let error equal math.subtract targets, comma, outputs. Now this is where we get a little bit into the weeds here. If, not math, matrix. I don't even know if I've implemented this function in my matrix library. So that's what I need to go and check. But this is where we're kind of like, oh my goodness, if we were using NumPy, we just use minus and it just works. Or maybe there's some other highly optimized JavaScript matrix math library that will do this for us. I'm going to get to all that. Yes, deeplearn.js is coming. But right now, I just want to do this in my code. Now, there's a little bit of awkwardness here. This is an array. So this comes out as an array. I actually want that to be a matrix. So it's a little bit awkward, but I'm going to say outputs equal outputs dot, matrix from array outputs. So this is me convert array to matrix object. And then the targets, the user is going to send that in as an array. So I'm also going to say targets equals matrix from array targets. So this is a bit of awkwardness because of the way that I developed my library that probably someday in the future I want to like refactor or rethink. But I need to have those things be matrix objects for me to be able to do this matrix subtraction. Now let's check the matrix library. I believe there's no subtract function. There is an add function which adds to the array. So this is so silly the way that I'm doing this because I probably in a real world, if I were really being thoughtful, I would make a comprehensive matrix library that has every possibility in it. But I'm just going to put in there what I need. So what I need is a static subtract function, and I'm going to have another, I'm going to call it other for the other matrix. Oh, no, matrix A and matrix B. So this should return a new matrix, A minus B. So a couple things. One is, if the rows and columns aren't the same, I want to do this element-wise, right? Basically, if you've forgotten what's going on here, basically I have a matrix like this, which has these guesses, 0.7, 0.4, and I have the known answers, 1, 0, and I want to take this matrix minus this matrix to give me one that has 0.3, negative 0.4. So let me add a function that does that. It's too bad I didn't have it from before. And I should do some error checking here, like check if the rows and columns are the same. I'll put that in later. Got to move along here. So that'll be in there maybe when you look at the code someday. But I'm just going to say I'm going to do first I need to make a result, which is a new matrix. Which is a new matrix that has the same number of rows and columns as either of them. I think I call it rows and columns, right? So I need to make a new matrix that has the same amount. And then I'm going to use my very silly loop function that I use over and over again to loop over all the elements and just say the result dot data index I, which is the row, index j equals a dot data index I j minus b dot data index I index j, right? So this is me just going through and subtracting everything from one to the other, and then I can return this result. All right, so I added this static subtract function. Is it silly to have a subtract function when I could just have an add function that then, add I could be used for subtract by just saying like multiply that whole matrix by -1, but whatever. I'm doing it as I'm doing it. We'll refactor later. All right, so now let's think about this. I'm going to comment this out, and I'm going to say, these are my inputs. Now I'm going to have my targets. And in this case, my neural network is 2, 2, 1. So I'm going to keep that. My target is just 1. I want to get 1. Now what I'm going to do is I want to say neural network. Instead of feed forward, I want to say train with these inputs and these targets. So let's just run the code and see if I get any errors. Then I'll debug the actual output. So let's go to the browser where I've kind of got this code runs. output is not defined, sketch.js line 11. Oh, there is no output now. Hey, no errors. Everything good. Good night. Thank you. I'm done. Forget about this neural network stuff. I can't. Oh yeah, I have more to do. I'm afraid to keep going, but I'm going to keep going. Let's just look in the training function and console log the inputs, the targets. Oh, let's just console log the error. Actually, I just do error.print. Sorry. So I can say outputs.print, because I have this print function, and targets.print and error.print. So I just want to look, I just want to examine all of these things. All right, I got an error. Error.print. All right, so, okay, something went wrong. So this is, this is the output. This is the target. This should be the difference. So what went wrong here in my subtract? Matrix.subtract targets, comma outputs. Let's look at this function. Something must be wrong here. Does anybody see? I'm looking. Does anybody see it? I, J, columns, rows, columns, A.data, A.rows, A.columns, return result, this dot rows. Oh, yes, thank you. All right, here's the mistake. This dot rows, this dot columns, that makes no sense. I'm writing a static function that's not called on an instance of a matrix object. I want to loop through everything. I've got to loop through everything in result or A and B. They should all have the same number of rows and columns. Thank you to Ruben in the chat who pointed that out to me. Okay, result.rows, result.columns. All right, now let's run this again. Great, this looks right. This is what the neural network produced. This is what this is the known output. And this is the error. And just to take this one step further, if I were to have two outputs, I don't know, and have a second target, this is matching what I've drawn over here, we could see these are the guess outputs, this is the target, and these are the errors. So we have now written into our code all of the pieces we need to get these two errors, get the output errors. The next step we need to do is calculate the hidden errors. I need to calculate the hidden errors. So looking at the code, I need another step here. I need to now say let hidden errors equal and figure that out. So what goes here? What goes here? This is the, and I suppose if I'm being consistent, I should say errors there, right? Errors are the out, and if I'm being really consistent, I should say output errors. Now what I need to do is calculate the hidden errors. Okay, so let's go back to here, and I want to do this with matrix math. So this looks like, hey, there could be some matrix math going on here, right? This looks like a weighted sum or something, dot product-y like looking thing. And here's the trick. This looks good, right? But what's all this like fraction stuff? Well, if you look at this, this is the same as this. This is the same as this. These are really normalizing. Dividing these weights by the sum of all the weights is a way of normalizing everything so that they all add up to 100%. But in the end, we're going to kind of like multiply everything by this learning rate constant anyway, so we could say like make a big step or make a small step. So that normalizing of it kind of doesn't matter. I mean, it's sort of important, but we can also ignore it. And that's kind of the trick here. We're going to just take out the, we know we want the amount of the error to be proportional, but But the fact that we're multiplying by its weight, it's going to be proportional. We don't have to divide it by the sum. So we can actually take the bottom out, and I'm going to say weight 1, 1 here. I'm going to say weight 1, 2 here. I'm going to say weight 2, 2 here. And I'm going to say weight 2, 1 here. And look at this. By golly, doesn't that look like some matrix math, right? That's got to be the result of some matrix product. Now, I need more space on the whiteboard. So what I'm going to do is kind of condense this a little bit. Well, 1, 1 times E1 plus weight of 2, 1 times E2. I'm going to make this take up less space. And then weight 1, 2 times E1 plus weight, what was that? 2, 2 times E2. Now, conveniently, I have this matrix here. And what matrix would I put here to get this, right? If I want the matrix product of these two matrices, I need to put a row in here. That's, right? The row, this row, W11, W21, the weighted sum, the dot product of this row and this column is exactly this. Now let's take this one. 1, 2, and weight 2, 2, right? Take this dot product with here, boom, we've got this. This matrix product, the matrix product between these two matrices is the hidden errors coming out of the hidden layer. This is very exciting. But there's something really strange here. It's like, stare at this. Now, all along, I keep getting my indices wrong, right? I've been getting my indices wrong in these tutorials. I had to do the tutorials over again. And this might look wrong, right? Because shouldn't it be row, column, row, column, row, column, row, column? This is row 1. Wait, why is there 2 there? It looks like I got it backwards. Well, the fact is, I did get them backwards. I got them backwards on purpose. This is actually this weight matrix transposed. So these weights are stored in a matrix already in my code. That matrix looks like this. Weight 1, 1, weight 1, 2. Weight 2, 1, weight 2, 2. Transpose this matrix to this and take the dot product with the errors and boom, I've got the hidden errors coming out. Okay, let's do that. This is working because it's square, but am I going to have an issue if it's not square? I didn't notice this when I was working this out. All right, anyway, let's go put that into our code. Oops. Yes, W superscript T. Okay. All right, the good news is, oops. All right. The good news is, I believe in the matrix library, I already wrote a function called transpose. I should be consistent. This function transpose returns a new matrix that's the transposition of the previous one. And so I should actually make this static. And it should require to receive it should receive some matrix object. And so it should be this. So I just changed this to be a static function so that what I can do is I can say here, back in the library, what do I need to transpose? I need to transpose the weights that are going from hidden to output. That's the weights HO. So I have this dot weights HO. So let hidden weights HO transpose. T for transpose. I could also just change the let who T. These are the naming. I could use some work on the naming, but these are the weights from hidden to output transposed equals matrix dot transpose this dot weights hidden output. So the hidden errors now should be matrix multiply output Wait, what did I say? If we look over here, matrix multiply that transposed matrix and those errors. That transposed matrix and the output errors. So this is calculate the hidden layer errors. Now, if I were writing a proper library that could support multiple layers, there'd be some kind of loop going on here, because I'd keep doing this from layer to layer to layer. But since I just have this 2-layer network, I'm just going to do the output layers, output errors, and the hidden errors, so that I can sort of get this backpropagation thing going in just one step. I'm getting a nice comment from the chat. I was worrying about the dimensions of my matrices, and Kay Weekman writes, the dimensions work out when going backwards, the transpose right. Of course, because I was worried about the dimensions not working, because the rows and columns have to match properly when you're doing matrix multiplication. But since I'm now going backwards, it actually makes sense that the matrices have to be transposed. You can pause and think about that for a second, but that does make sense now. Okay, so I think I've come, I was also, if you're looking at this notation in like a textbook or something, you'll often see if you have a weight matrix that's W, and maybe it's like Wij for rows and columns, you'll often see T in the superscript as, and you can't see that. I'll write it over here, right? If this is the weight matrix W, and you have columns and rows, then you'll often see a superscript of T, and that refers to this matrix transposed. And so maybe this would be, weight HOT or something. I don't know. So my notation, as you all know, is kind of poor, but I try to do my best to explain it, and hopefully it will match up with other notation that you see and that sort of thing. Okay, so this is now done in terms of backpropagation. I've computed the error. I've propagated that error backwards to compute the hidden layers error. And now I just need to add the part where I adjust all of the weights, these weights based on this error and these weights based on this error. And then we just move on, and then we're done. So I'm going to do that in the next video. I should warn you that the math for doing that is this, which I'll discuss in sort of generalities, the math of gradient descent for finding these delta weights is pretty complicated. I have 2 videos that I've made where I kind of do something similar, which I will reference, as well as all of those 3 blue, 1 brown videos that go through the math in detail. I'll probably start the next video just by presenting the formula and then implementing, kind of talking through the pieces of the formula and then implementing that in code. Okay. Right. People are telling me I don't need the IJ. Yeah, I don't need the IJ. But anyway, lowercase t, uppercase T. So now what I need to do is I need to, where am I in my notes? And what time is it? Oh, it's 12:35. Remember how I said I was going to be done with backpropagation by 12:30? That didn't happen. That's okay though. These notes are done. All right. All right. So I think, does everybody feel okay? Let's get a snapshot of the whiteboard as is. I think I'm going to erase this now because what error do I have? Result equals new matrix, this dot columns, this dot row. Oh, where? Where do I need to change that? Sorry, I'm seeing something in the chat that I got columns and rows incorrect somewhere. I think I have that here. In the static transpose. No, this is correct because, but you might think this is incorrect, but I have written my matrix library in such a way that the rows and columns come in first. So if you're transposing it, you send the columns in first and the rows second. So I think that's correct. I'll let and see if anybody, I'm going to give it a minute. So what I need to do now is find the best notation for writing out the formula. And this is where I kind of got stuck in my preparation for today, although I have to say, preparing really helps. I can't use this on static. Ah. Oh, I see. Thank you. Here. Got it. What's the best way? I'll just do this at the beginning of the next video. Shoot. As I didn't try to, I would have gotten this error if I tried to run the code. Let's add something to the end. Nah, it's fine. Just do it at the beginning. Yeah. I got it, everybody. I'm just trying to figure out where to. No, I haven't updated the weight. Simon is asking, have you updated the weights? No, there's a whole big step here. I mean, kind of like, I just did the sort of like beginning part. So there's a whole big step. So I guess I'll just cop to this error at the beginning of the next video. So what I'm trying to do, I'm going to erase the whiteboard. I don't think this has any value anymore, or at least this whole bottom part doesn't. I can leave this diagram here, maybe for reference. So let me try doing that. And let me try to find a way of noting the formula for updating the weights. This I'm going to need to try twice, or I'm not going to. So this is my thinking, and I'm going to kind of use my notes here a little bit. I'm going to need help with everybody, oh, that's just the mouse. I was like, there's a black mark on the whiteboard. So I will correct this, by the way, at the beginning of the next video. Let me just make sure the whiteboard is dry. So my thinking is any given weight equals its weight plus a change in weight, right? And so the thing we're trying to calculate is this. Another way of, and the way that we're going to calculate this is by thinking about the way when you we want to understand, like, we want to adjust the weights. We want to adjust the weights. So, we want to think about this as the change in error based on the change in weights. So how does right, if I know how the error changes based on I'm just sort of thinking this through based on how the weight changes, right? This is the whole gradient descent thing. Then basically I'm saying delta, I want to take the weight and minimize the error. So adjust it based on the negative direction of how the error changes based on the weight. And this error is something different. It's actually the cumulative cost. So that's the kind of squares of all the errors. Let's see if I'm getting this about right. And so that question becomes, how do I know how the error changes based on the weights? And that is the formula that I've kind of derived previously is the error times so in this case, right, if this is the output, the derivative of the output based on the weight. I'm talking this through. I'm going to come back and explain it. Let's see if everything I'm going to do this again. I'm just kind of like talking this through into my head. And so now what I need to do is figure this out. And what this is output is sigmoid, right, of the weighted sum. How did I write this down? I just wrote weighted sum on my notes. We can think of the weighted sum of all the connections coming in, but I could just call that like x for a second. And so, and the derivative of sigmoid is a known thing. The derivative of sigmoid x equals sigmoid of x times 1 minus sigmoid of x. I know it looks like a 6. And so basically, if I put this here, I kind of have the formula for any given single weight. Let's look at this chat. So this I think is right. That's where my notes end. Let me look at the code that I did. So that's really like the gradient. So you can think of this, would it be correct to refer to this kind of as the gradient? And since I need to do that for everything, how can I notate this with matrix math? I know that what I do in my code is I take the hidden outputs transposed. I need more room on the whiteboard. All right. Let me get this far. So I think what I want to do is try to get this far for a single weight. Then I'll erase and try to get further with, turn this into matrices. Anybody have any corrections or notes or thoughts you want to add to what I'm going to erase this and kind of go through it, but actually like try to explain it a bit more as I do that. I mean, I could just include the final formula at the top. Maybe I should write that down. I don't see output equals matrix. I don't see anybody talking about what I'm doing right now in the chat. Everyone's just talking amongst themselves. All right, so I think we just need to figure it out for any one of these given weights, how to adjust it based on the error. And we've calculated all the error stuff already. Okay. Just looking at this. All right, I'm going to start with a single weight. All right. I'm looking in the chat. I see some people are typing in the Slack patron group. I might not get to be honest, the challenge today. I think I can. All right. I'm just going to move forward. I'm going to erase all this. I'm going to try to explain it again. I forgot where I was. I just finished a video, right? Okay. Oh, yes, the error function, meaning the cost of all of the sum squared of all the errors. A squaring, yeah, I do need to talk about that. Yes, thank you. Okay, I definitely will mention that. All right, so in this video, I'm going to start to talk through learning with gradient descent. We've looked at how to back propagate the error that's coming from the output back through the network. Now we need to look at how do we turn all the dials. Now, but before I get to that, I did make a sort of major mistake in the previous video where I was making this transpose function and turning it into static. So the word this now means nothing. So I need to make the resulting transposed matrix out of the one that's being passed in. So I just wanted to correct that right here at the beginning of this video quickly. Okay, now, so there's a few things we need to talk about. So first, I want to talk about what is this thing called gradient descent. Now, let me, once again, as I always do, reference that other materials will go to this in more depth. I made a video called The Mathematics of Gradient Descent. I don't really recommend that one as my top choice, but you could go watch that. And I also reference the one they do recommend, which is the 3 blue 1 brown video about gradient descent, and there's a nice Siraj video about gradient descent too. I'll link to both of those in this video's description. But the basic idea is that we need to come up with a cost function. What is the cost function? Well, if this is an error, this is like an error vector, right? 0.3 and negative 0.4. What we want to do is we actually want to look at the cumulative error over time of many training examples. So if we say like, here's 100 pieces of data with known labeled answers, what's your cumulative error over all of them? And the way that that's typically calculated is by the sum, which is often used this nice uppercase sigma. Is that uppercase the right thing to say with Greek letters? The sum of all of the targets minus output squared. So this is often referred to as a cost function. And you could graph this function. Like you could imagine it as like a function like y equals x squared. And if I had a function like y equals x squared, it would look at this. And if I wanted to minimize that function, I would have to start moving. I would want to like look at how do I go down? How do I go down towards 0? How do I walk down? Gradient descent. And how do I know the direction of the slope of this function at any given point with a concept known as the derivative? So again, I would refer you to some videos from 3 blue 1 brown that go through the calculus. What is a derivative? What is gradient descent in more detail? But this is the basic idea. I want to push the weights. I want to know what happens, right? When I change the weight, how does that affect the error? The change in the error based on the change in the weights, right? I want to minimize the error. I want to change the weights in the direction that changes the error. This is kind of the notation for that. The change in error relative to the change in weights. And the concept of derivative is more sophisticated than that, but that's a way of thinking of it right now. There's something else I wanted to mention about this. Yes. So here's the thing. This is a nice little like graph of y equal x squared and sort of some notation over here. But the thing that's really crazy about this is we aren't living in two-dimensional. This would work if we have a single output. This is what it would look like. If there were 2 outputs, then we might have this like bowl, perhaps, I think. If there were 3 outputs, oh, I'm lost. I can't think. We're going to get into crazy n-dimensional spaces that you can't really imagine. So that's one thing that's really confusing about this is these outputs could be many, many. So we really have to, in a way, tackle them one at a time. Like, how would it work for just one? And then, in essence, we're going to do the same thing to all of them by pushing them through some matrix math. So that's ultimately what I'm going to do. I'm going to explain a little bit further, but eventually, again, I'm going to be glossing over some details and mostly focused on trying to implement this in the code. All right, let me pause for a second. I'm not seeing anyone yelling at me that I said anything horribly wrong. So that's the thing that I wanted, the error function. Thank you, Kay Weekron, for reminding me about that. That's where I wanted to start. Okay. So Where's the actual eraser? Okay. Now that we've talked about this sort of cost function, how we're trying to minimize that function using gradient descent, walking along the graph of that function towards the bottom, let's talk about how we actually do that. What's the thing we're actually trying to calculate? Well, what we want to do as we sort of look at all this training data is we want to say, how do I want to change a weight? I want any given weight, this W for any given weight, just one weight in the system. I want to, the process that I'm going to run in my code is to change that weight by some delta weight, the change in weight. So here we are. I should be able to just say, if I could just figure out the formula for delta weight, I'm done. All right, well, I did say that I did just a moment ago talk about the cost function and the idea of how does the error change when I adjust the weights. Well, this is really another way of saying delta weight. If I said delta weight is, how does the error change when I change the weight? If it gets bigger when I change the weight, I want the error to get smaller. So I could kind of say delta weight is negative how the error changes when I change the weight. So this is just another way of kind of writing the same thing. People who know more about mathematics might be getting upset with me right now. I will look forward to your comments. All right, so now let's think about this. How do I calculate this? So how do I know how the error changes when I change the weight? Well, this is something that I have gone through in my gradient descent video. What I can do here is actually just say, I'm looking at my notes. Oh, I forgot about the learning rate. Sorry. I should add one more thing in here, which is that this delta weight can also be a factor. I can also factor in this thing called a learning rate. I'm going to kind of fold this in at the end, but the learning rate is just like, this is how much this is the direction that I need to move. Should I just move like a tiny bit, or should I move like a lot? And so you've seen this again in the simple perceptron example, this idea of a learning rate. So that should get folded in here as well. So basically what I'm doing here is I'm saying this is a formula that I've derived in other places. This should equal, I'm looking at my notes over here just to see if I get this right, negative the error itself times how the output changes when I change a weight. So I'm going to call that dO dW. How does the output change when I change the weight? Well, what is the output? That's something we know. We've been working on that, right? The output of any given neuron is the weighted sum of everything coming in passed through the sigmoid function. And again, sigmoid is kind of a historical activation function that's not used as much right now. And later, we can swap in other activation functions and things. But one of the reasons why it's useful to use sigmoid is it makes doing this calculation kind of easy. So if the output, the function that's the output, is equal to sigmoid, and that's the lowercase Greek letter sigma. I'm trying to write this out. Maybe I should just write the word sigmoid. I'm going to write it as sig, S-I-G. Sigmoid of that whole weighted sum of everything. Let's just call that x for a second. Then, if this is the output function, how that output changes when I change a weight is the derivative of that function, right? On any given weight, right? That this is the weighted sum. How I change these weights, what is the slope of that function in this crazy n-dimensional space? Well, it just so happens, if we go back to Wikipedia, sigmoid derivative, derivative, where is it on here? It's so nice. Man, it's not on here. Fail. Little failed moment here. Let's find a different place. I don't want to derive it. Just want to look at it. Yeah, here it is. Okay, that's a nice little. Oh, wait. Hold on, I'm getting some good questions. Maybe add a factor of 1/2 to make the derivative the error. Oh yeah. Yeah. So wait, where do I add that? You mean add it in here? Because this thing is, the derivative error is actually, the errors are squared or something? Is that what you meant, K. Weekman? I always just lop that off because it's just another constant in the system. I think you should do, Eric in the chat writes, I think you should do a pass propagating errors back through the whole network, then update the weights. It doesn't matter much now, but if you did have more layers, you would be able to update all the weights in parallel, language permitting. I think that's kind of what I did already, or I'm trying to do, but I see what you're saying. Right, because I already did this step of passing the errors back, and so now I just want to do update these weights and update these weights. I already have these errors, so update. So I need to fill in the updates here and the updates here. That's what I'm trying to do. Okay. Maybe I missed it in the stream. Why is delta weight in the first formula using the uppercase delta, but in the second formula, uppercase delta weight equals to negative lowercase delta e over lowercase delta w? I mean, it's really the same. Yeah, my notation is kind of bad, but I mean, I really sort of mean this as shorthand for this, in a way. In the cost function. Yeah, in the cost function. Okay. I'm sorry, I'm just reading the chat for a second. Right, I was looking for a nice derivative of sigmoid. Okay, hold on. If anybody has a suggestion for a nice web page that's gonna, I mean, I guess I should just use this one. It's just like, this is a little janky, but yeah, it's deriving it. No, I know what the sigmoid derivative is. I just wanted to like find a web page that confirms it for me. Maybe Math World, sigmoid derivative. Yeah, there we go. All right, I'm just going to... Yeah, Ruben, I did sort of mention that, I believe, during a bunch of times, and I will continue to mention that. All right, Wolfram alpha. Wolfram alpha. What is the derivative of sigmoid? And I cannot spell derivative. All these web pages are making me sad. I mean, that's a nice way of putting it, but okay. I don't need a diagram. Gosh darn it. I'll come back over here. All right. Shoot. Yeah, I will. Yeah, no, I'm definitely not doing the derivation. I just wanted to confirm that I was correct. So we can, here I am now on a web page which shows the derivative of sigmoid, and this is what's really nice about it. The derivative of sigmoid is actually sigmoid times 1 minus sigmoid. So that's what makes kind of working this out once I start to plug the math into my actual source code kind of easy. So if I come back over here, I can say this is times sigmoid of the output minus, times 1 minus sigmoid of the output. I don't know why I put. So this is basically what I'm looking at here. If I want to change any given weight, I change it based on the derivative of sigmoid multiplied by the error. And this is the same formula that's appeared in several other of my previous videos, and one that you can kind of dive deeper in with some of the links that I've included in this video's description. The big question now is, I'm really just talking about the case of changing one weight. How do I turn this into matrix math? All right. All right. So now, again, this is where my notes have ended, and I need a way of writing this with matrix math. And the way that I'm going to do that if anybody wants to help me with this, I would gladly take your help. Oh, I forgot about the 1/2 thing. I'll bring that up. I'll bring that up next. Let me see. Is there a notation that's used in... Okay, this is the notation that is used in the Tariq Rashid book. So let me try to write that out. Dare I erase this top? I think that's what I have to erase now. So let's look at this notation. Delta weight for, and he uses JK. I've been using IJ, so I'm going to keep that. I know that's JK is much better. Equals, we have the learning rate I've talked about, which times the error vector, which is J, right? Because it's it's like one. I'm iterating over the rows, so it should be so confusing. Just going to say the error vector times sigmoid of the output vector. Sigmoid of the output vector. This is the same thing that I've got right here. This is the same notation. I'm just confirming that I'm right. Times 1 minus sigmoid of the output. The question is, if I'm thinking of this as rows, columns, and things are being transposed, what's the index that should go under E and under O? That's a question. Oh my goodness, wrong camera, wrong camera, wrong camera, wrong camera. So long with the wrong camera. And I wrote up, let me do this again. Sorry everybody, this is good. I need multiple tries at this anyway. I'm writing off the whiteboard. So I'm looking at the notation that's in the Tariq Rashid book, and this is what's written. JK equals the learning rate. I'm changing something. Learning rate times E sub k times sigmoid of O sub k times 1 minus sigmoid of O sub k. And again, I'm going up to high. Times, sigmoid, let me make sure you can see this, of O sub k times sigmoid, times 1 minus sigmoid of O sub k. So this is the formula as written in, oh, and then this whole thing, right, this is why, what did I miss? I missed this whole thing now. And I'm running out of space. So I'll figure this out, is the matrix product, right, which my symbol for that is like a train. The matrix product with the transposed output J. So this is what's written into the Tariq Rashid book. What I would like to do is try to match this with what I've done so far. So in theory, except I think, Tariq, one of the things that I noticed is the Tariq Rashid book, I'm pretty sure, does columns, rows. That's why I'm getting confused. So my notation has been rows, columns, and this is a single column vector. Yeah, okay. And then this is transposed, so it would be J. There we go. So this would match there. And so right, that's the bias derivative if I don't multiply it with the activations as well. So what's the step? So why is it that when I explain this, why is it that I went through this delta weight and I didn't include, I forgot to actually multiply it by the output here? Because, oh, is that because of the negative 1/2 thing, and then I'm taking the 1/2 thing and I'm taking that out, but with the bias it's just 1, and so that goes away? This is comfortable for me, and then I'm going to be able to turn this into code. But I'm kind of confused as to, I mean, I get that this needs to be here, but I'm trying to think of what's a nice way of explaining how I missed just doing it as the matrix product with these, oh, but it always is multiplied by that. Well, how come I missed it down here? Was that just my own mistake? I'm going to go check out some things that are being typed. Yeah, we believe in the chat writes, why am I watching this? I'm just learning to make the ellipse in JS. Yeah, go back to that. Don't get out while you can. All right, I'm just going to, Dan, if you already calculated the sigmoid in the outputs, you can just do x times 1 minus x. Target is the derivative in the last layer. Predicted minus target. There's a lot of interesting things being discussed in the chat. All right. I'm just going to... and hold on, I'm looking at the... Oh, this camera went off. I need to do some more reading and preparing. Maybe I'll have to just be done for today, and I will... Errors in where it's in output. Hold on, just... I wish I had that gradient descent formula. Let's see here. I think in this video, if I could find the part of this video, right? I'm doing it here. I'm basically going through exactly what I'm trying to go through now. Yeah. Hold on, I just so close to finding the right point in this video. I think actually this might help if I kind of match it up with the diagram in this video. Yes, you are watching a live stream of a person looking back in a video tutorial that they previously made to try to find something to help understand the video tutorial that they're trying to make right now. That is one day, that is exactly what you were doing. And you should all just, there it is. Here it is, down here. Please step away from the...
Partial derivative this, it all boils down to just... Finally, we get this, error times x. That's what should go here in delta m. Guess what? Let's go back over to our code.
I did all this. I went through this. You know, another way for me to do this is actually, now that I'm realizing this, is just, all right, so what I'm going to write.
Finally, we get this, error times x. That's what should go here in delta m.
Error times x. This is the equivalent of x. This is obviously the error. And the new thing here is the fact that I have sigmoid as the activation function, right? So in this, the difference is, in here, there was no sigmoid function, so the derivative was much simpler and doesn't show up, right? Right? Can I make an argument? Can I stop where I am right now and connect this here with this video where I derive this formula for the change in weights? The derivative is 1 in your video. Yes, I think that's right. All right, so this is what I'm going to do. I see K. Weekman is typing, so I must wait. K. Weekman usually has something very wise to say. Shouldn't that be the hidden layer activations we multiply by? Yes, the hidden layer activations. I mean, it depends where I am. Oh, I got rid of my diagram. Right now, I'm not doing the... it would be multiplying by the hidden layer activations. This is just like... What I'm doing right now is generically for any connection. And then I'm going to do the same for the output and the same for the hidden layer. But the output uses the error vector from the output, and the hidden layer uses the error vector of the hidden errors. So yeah. All right. 2 times target minus W index I times... Yeah, exactly. Yeah, I just erased that. I know. On purpose. All right. I'm going to go back into the video tutorial, and we'll see what happens. I just took a little break staring at this. I'm having this moment of like, haven't I gone through all of this before? And then I realized, I kind of referenced before, I haven't. So I went back and looked. So what I want to do right now is like, this is where I've sort of ended here in trying to sort of look at how the error changes based on when the weights change. That I've talked about this in my mathematics of gradient descent. And in this mathematics of gradient descent video, there was no sigmoid function. So ultimately what I have here is, and this is sort of 18 minutes into this video, which boils down to the chain. And by the way, one thing that I missed over here is the 2 or the 1/2. Sometimes when you take the derivative of something squared, you get a 2, and so you divide by 2 or multiply 2. So I just sort of like take those out, but because it's just a constant, I'm going to have the learning rate later anyway. So, but that's why you see the 2 over here. But what you see here is change, right? The change in the weights. This is m and b for a single, and this is really for a single weight. Y equals mx plus b, the bias. I haven't gotten to that yet. Is the error times the x times the learning rate. And that's ultimately what I have here. But so I have this book. So let me now write this out with sort of more matrix notation. This is make your own neural network. I'm going to basically use the exact, and I would highly recommend kind of reading this chapter along. I'm going to use basically the exact same note. What I want to calculate is the change in weights for every weight in the matrix of connections, every row and every column. And what I want that to be, I got to be a little bit lower here. This is, based on what I kind of worked out here, well, I have the learning rate multiplied by the errors. And the error vector, right, the error vector is a single column vector. So I'm looking at all the different rows. Times the actual output. Sorry, hold on. If I come back to here, this is basically, sorry. So let's, just looking at this right now, let's go back to my previous video. That's basically the same thing as I've got right here. I've got the change in weight is the error there, times the learning rate. But there's an x in there. So the x, what's the x over here? Well, the x is actually that output. So I'm going to have to do the matrix product, which my symbol for that is a trade, but I'm going to use a dot right now, with the actual output itself. But the thing that's missing in this particular scenario is I didn't have the sigmoid function. That's how I need to look, which way do I go, which way do I adjust based on those activations are coming from the sigmoid function. So I need the derivative of the sigmoid function here. So I also need to say sigmoid of the output, that output is a single column vector, times 1 minus sigmoid of the output, which is that one column vector. And now I take the matrix product with the actual output itself. Now here's the thing. This is something we've actually calculated already. In my code, I calculated the outputs. I did that while I was feeding forward through the network. So this is actually something that's already calculated, and I just need to put it in here. So this now, if I can just take this delta weights, then I could say for every weight ij, adjust it by its corresponding delta weight ij. So this is now the formula that I need to implement in my code. I need to implement this in my code to calculate all of the delta weights. How do I change all of those weights for every single weight? Whether it's, and this error and this output, this could be the final output and the final error, or this could be the hidden output and the hidden error. Same formula is going to work. And now, of course, I'll do the bias as well. But here, now, I think I could put this into my code now. Yes. Oh, okay. So, and in fact, I'm doing something really weird here. So this is really, I can simplify this even further, right? Because the activation function is inherent. It's already been calculated. So I really should say just that output vector times 1 minus that output vector. And this is going to have to be transposed so that because of the way the matrix products worked out. But let's get to that when I get into the code. Okay. I should go back. I think I should go. Maybe I should try explaining this again. Why is it This is definitely going to require a second shot. Let me go into the code, and if I have to redo this next week, I will. So I have to watch this back and then figure out where my explanations went awry. I can already hear Mathieu telling me. The last O should be H, I think. Oh, yes. Yes, thank you. Ah, that's it. That's what I've got wrong. Maybe this is salvageable. Yeah, this is H. Thank you. That's definitely H. Yeah, why does it say O in the in the book here? That's interesting. Okay. Let me try this whole explanation again. I don't remember where. It comes from differentiating the inner function, which depends on the previous layer, i.e. the hidden. Okay. Sum of squared each error. Okay. Do I dare? Let me start over. I almost did the last bit. I just put this in the code and then, whoa. Oh, I'm in the wrong. I thought I was in the whiteboard because this screen has a shot of a whiteboard on it. We're almost done. I'm almost in the last bit where I could just put the code in. Oh, it's 1:30. I have to go. Shoot. Let me see. Maybe I'll come back. I don't have time to go to this conference. Oh. Let's see if I can. Let me try this explanation one more time. This is definitely I have to come back and continue this another time, like next week. But I'm so close to the end because once I just get that formula written correctly out there, I could just put it in the code. Because basically, yeah. Skip the conference, time for a challenge. I know, I need to do a coding challenge. I'm not going to have a coding challenge today. because of backpropagation. Backpropagation. All right. Just thinking for a second, where I spent so much time, like the momentum has totally died. Okay. I'm gonna go back to where I referenced that previous video. No, that was fine. So I referenced that previous video. I came over here, blah, 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 and then I went back there. Okay. All right, so what I want to do now, so where am I? I had this formula. I realized it's similar to my previous video. I know I'm just repeating myself, but which is over here. Now what I need to do is take that formula that I've gone through and let me actually just take it and write it directly from this book, basically. Oh, no, you know what I'm going to do? Let's just implement the code. Oh, shoot. Give me one more chance here. So I'm reading the chat. I can't believe there are people here still watching. All right. So after I reference this video, so let's try to take this now and turn this into matrix math. Basically, remember what I want to do is I need to know the change in weight for every weight that's in our weight matrix. And so this is exactly the same formula that I did in the gradient descent video. It's basically what's down here, but let's kind of rewrite it with some notation. And thank you again to this book that I'm kind of also pulling from. So if I want to know the change in weight for every weight in our row column matrix, row I, column J, this equals, referring back over here, okay, well first we need the learning rate, times the error, right? The error, now the error is a single column vector, right? So it's just rows. Now, this could be the error of, again, these are the change in weights for any weight matrix anywhere in the network. So this error could be the final output error, or it could be the hidden error. And then I need to use the sigmoid function. So the derivative of the sigmoid function, that's the piece that's missing over here, right? Oh, shoot. Sorry. And then I need to multiply the actual output itself from the previous layer, whatever those. I need to multiply by the inputs itself. That's why x is over here. So let's make the case where I'm doing the weight adjustments for the final layer. We're gonna so I need to multiply this by that. And actually, that's going to be the matrix product, which I don't have a symbol for. Good thing you can't see it. I'm trying to write it. I need to buy those hidden outputs. So I need to, what's coming out of the hidden layer, that's x. So I'm going to put that here. And so now, but I need to also figure out which direction to go. I need the derivative. I didn't have the sigmoid function in this video, so it's not there in the formula. But now what I need is this. And guess what? I already have this. This is just the output itself, right? So the derivative of the output of the final output is the sigmoid of the weighted sum of everything. And so now the derivative is O index I, that single column vector output, times 1 minus O. So this is actually the entire formula I need. This terrible, terrible, terrible me who has written this too high on the whiteboard. I am hereby fired from ever making a YouTube video again. I'm gonna rewrite it a little bit lower because we've really got this now. We've really got this delta weight formula. I should have just shown you this, right? I need to take the learning rate multiplied by the errors, which I said was I, multiplied by the output, multiplied by 1 minus the output. And this whole thing now gets the matrix product of what was the x in this situation. If this is the final output of the network, then this becomes the hidden. And this is the matrix product. This is the delta weight. Oh, look at this. Oh, I love this now. This is the delta weight for hidden to output. The delta weight for input to hidden then equals the learning rate times the hidden errors times the hidden output times 1 minus the hidden output, and that whole dot product with the input itself, which I'm going to call x. So this is how I adjust the weights. This is why I need, oh my goodness, this is what I spent all those other videos on, just figuring out what this hidden error is. This is really the magic of backpropagation right here. So these are the formulas. You know, are these formulas, are they going to make sense to you, especially with this mess of a video that I've put together? Probably not. But we kind of have arrived at them. But the thing, but I am, it's such a cop-out. Do these formulas make total, complete sense to you? Well, hopefully, again, the idea is to look at this and kind of get an intuitive understanding, right? We know we need to adjust the weights based on the error. The hidden error is kind of like a way of getting the portion of that final error. We know we need to adjust them in the direction of... Oh, I'm just looking at the chat every once in a while. Do these formulas really make any sense to you? Probably not. If you want to kind of unpack them further, I think you could pause now and go back and kind of watch my mathematics and gradient descent video, look at the 3 blue, 1 brown videos. But the pieces of this should really make sense, right? We know we want to change all the weights. We want to adjust those dials to get a better output. That output is based on the error. That error is backpropagated to a hidden error if we're going back weights in the matrix. The derivative of the sigmoid function is important because it tells us the direction of which how things are being activated. And then, of course, we need the what's kind of come before. Hidden comes before the final output, and the input comes before the hidden. This is exactly what I've done in the previous videos of when I had when we were looking at y equals mx plus b. So we can connect that back to the gradient descent video. Okay, so I think it's time. I'm going to stop right now, and I'm going to, from here, implement this in code. All right, so probably what I need to do is redo the explanation, because I think I've really botched that. But I think I think this is right enough that I can put this in the code, and maybe we've actually got our neural network code. I don't know what backpropagation means. So I'm gonna have to return to this. I've run out of time today, but let's see if I can at least put this in my code. I'm not even gonna do this as a video tutorial. I'm gonna just come back to this last piece. So I think I need to redo the videos. I'm realizing today, redo the videos where I explain, these won't be the final published ones, the delta weights, how that's calculated. But let's just see if this kind of matches up really quickly. So if I'm doing this one here, so here's the thing. Let me save this as old. And then, so I know where I last left it. So a couple things I need. I need a function called d-sigmoid. And that is, if I have let y equal sigmoid of x, now I return y times 1 minus y. So this I'm going to need is the derivative of sigmoid of function. I think this is going to like mess. The problem is I want to use this stuff. So I think instead of doing feed forward, what I can actually do here is do this. And then I was calling these outputs. Yeah, this is the autocomplete that I guess I don't want. And then I don't need this anymore. So targets, though, I do need. So what I just did is put the whole feed forward in here thing, because I need to, and then I need to calculate delta. The idea is to calculate delta weights. And so how do I do that? What are the pieces that I need? The pieces I need are the error. This is the, so I have this. And now I need to multiply it by this. And that's an element-wise multiplication, right? So I actually want to say, right, this is mapped through sigmoid already right there. So I want to say, like, I'll just call it D outputs for right now, equals, so I need to make a copy of it. So I need to like, did I have a mistake here? Yeah, no, that's fine. I'm going to come back. I'm going to come back to this next week. I kind of wanted to put the code in here. So the derivative of the outputs, if I can take so if I take a function called 1 minus, yeah, actually the outputs already have, so the thing is, I need a like already sigmoided function, which just does this, right? Because it's d-sigmoid if I'm looking at the stuff that's already been sigmoided. Let's just put this up here. Again, this is going to be a mess. I just want to put the code in here, and then I'm going to have like some time to think about it. I'll come back and do another live stream where I finish this. Whoops. So I want to say matrix.map the outputs. Right? I want to, because they've already been sigmoided, map already sigmoided. Outputs already sigmoided. So I'm going to need a map function that's static to make a new vector. Where's map? Static map matrix, and let result equal a new matrix, matrix.rows, matrix.cols. Sorry, I'm going to do a lot of stuff without really explaining it right now fully, just to try to function value and then return result. So now I have this. So I have this. Now I need this, right? And I have that. But those get multiplied by each other just element-wise. So can I say D outputs, that's the Hadamard. Hadamard, how do you say that again? Hadamard product. I'm going to write a Hadamard function with the output errors. Right? So this is the Hadamard. And so if I put that into the library, did I actually? Oh, there is a scalar product. That's the Hadamard. So that should be called probably Hadamard. But whatever. It's called multiply. It's already in the library. Just because I have to go, I'm kind of like race through this. I can multiply it by the learning rate. There also should be, how come my library doesn't check to see if it's a just a single number? Oh no, that's only the scalar product. That multiply function is only doing the scalar product. Got it, got it, got it. Oh, I had it previously doing the, so I can adjust this to do Hadamard. I need to do that. I see, I see. So if n is an instance of a matrix, now I should do the Hadamard product. Otherwise, just do the scalar product, which is different than the matrix product, which also is called multiply. So the naming is terrible here. But so that would be this. So now, okay, so that works. Multiply by the learning rate. So I'm just going to say, I'm just going to have that be a constant here right now. Not a constant because I'll use let. Let learning rate equal 0.1 or something. Okay. So this, oh, this went off. So I did this component, this component, this component. Now it needs to do the matrix product with, but that has to be transposed. So now what I need to do is say let this actually transpose. No. Where am I? I'm here. Yeah, targets from outputs. Now I need to just take this here. I need to take these. Let hidden t equal matrix dot transpose hidden. Hidden t. Right. This is the matrix transposed, and then a delta. So this is really, what I should really say is like sigmoid, no. Yeah, D outputs. Yeah, sorry. So now let delta weights equal matrix dot multiply D outputs hidden transpose. Delta weights dot print. Then all right. Simon is asking why practice in a live stream. I don't have a good reason. Just because I'm already live streaming, I need to practice. And maybe this will help. Okay. Sorry for everybody sort of joining in the middle. I've run out of time and I have to go, so I was just trying to like see if I was in the right path. I need to double back and redo the video explanation. I need to watch my gradient descent video to connect it better, and then kind of just present these formulas. I think that makes more sense. I can make this much shorter. I just wanted to see if this would actually work in the code. I don't have time to test it out. And then so now we would say this dot weights, which is hidden to output dot add delta weights. So this is change hidden to output weights gradient descent. Okay. Now, all right, so I think I'm going to finish up here. I just wanted to, so what I'm going to do, better than no practice, exactly. So I don't know if I've gotten this right. I need to stop freeze frame here for myself. Sorry that this live stream is kind of ending abruptly and I didn't even do a coding challenge. These are the formulas that I've arrived at for how to change the weights between hidden and output and how to change the weights between input and hidden. I need to come back and redo my explanation. I think everything was fine all the way up until the sort of I got to the point where I started with this line right here. So that is where I'm going to return the next time I come back, hopefully sometime early next week, to continue this live stream that's not finished. I'm going to start from here. I'm going to try to derive is the wrong one. I'm definitely not going to derive. I'm going to start from here, present these formulas, kind of understand them as they relate to my previous gradient descent videos. Then I am going to put that into the code here to see if I got it right. So, but what I need to do, I need to finish this code and then test it. So I'm gonna freeze frame this. I will publish this somewhere. Let's publish this somewhere right now. When the archive for this live stream gets posted, which is typically sometime this weekend, I will include a link to just like a Google Drive folder with this code in progress. So if anybody wants to like try to keep working on it or like check what I've got so far and refer to it, you'll be able to. I'm not going to put this code up in GitHub exactly. I mean, I will eventually. Ostensibly, this is the same as what I already have in my, this should be basically, I'm redoing, I think there were mistakes in here, this exact function. Neural network prototype train. This is a version that I made last spring. And you can kind of see there's some similar stuff. But I kind of started over from scratch. So this is the end for today. It's 1:50. I definitely have to be out of here. I'm sorry that I didn't get as far as I wanted to. The next steps are, I knew this would be hard. The next steps are redo my gradient descent video. Maybe I'll put this into some notes up here. Next to do. Redo gradient descent video about delta weight formulas. Connect to mathematics of gradient descent video. Okay. Then implement gradient descent in library. At some point I need to talk about different activation functions. Then do XOR coding challenge. And then MNIST coding challenge. All right. So this is what I got to do next. Thank you, everybody, for being here today. This is really, I don't know, I was going to say this is kind of different than what I usually do, but to be honest, it's exactly what I always do, which is I'm trying to learn something. It's different in the sense that I do sometimes do videos about stuff that I guess I know a little better or that are a little simpler that I've been working with for 10 years or something. This is like, I don't really know what I'm doing. So I'm really trying to learn and get a sense of the mathematics of building a simple neural network and how to implement that with my own code so that I can later work from a higher level and feel comfortable with the sort of language of all this stuff. So this is all I had time for today. I would say that I'd come back and finish this later this afternoon, but I know for a fact that it's not going to happen. Because that if anyone wants to join the Patreon to discuss this more in the Slack group, you're welcome to. Maybe you don't want to after watching this live stream. But I'm going to be busy for the rest of today and tomorrow with this Processing Foundation and SFPC Learn to Teach, where I'm going to talk about how much of a disaster my video stuff is. Okay? Thanks. Sorry I don't have time to really answer questions. And there will be some new videos continuing this stuff that get published, and the coding challenges will come as well. Any last words? I got a few donations from the chat. That's very nice. Let me see if I can. Where do I check that? Here. No, this is where I send a super chat. Oh, can I see it in my live dashboard so I can thank the people? By the way, it's wonderful that people donate through the YouTube super chat. My preference is as a way of supporting the channel is through Patreon, but obviously not everyone can do that, so that's wonderful too. Where can I find them? There's nowhere where I can see to find them. I know I can see them later once I finish, and there's a place in my Creator Studio where I can go back and see them, but I'd love to be able to thank the people right now. If anybody... by the way, those of you saying nice things to me in the chat, I really appreciate it. It actually, it does mean a lot. It does help me. I mean, you shouldn't say it if you don't mean it. But if you did actually learn something and you think this isn't so terrible and you say something nice about it, that does help. And I absolutely welcome. I've gotten lots of wonderful constructive criticism on ways I can make the videos better and that kind of thing too. So Socrates says, I donated $5. Thank you, Socrates. Yeah, okay. So this is part one of this. This is part one of this week's episode. It will be continued next week, hopefully before next Friday. But it might just be that next Friday I do the continuation of this. We shall see. I actually have a makeup class I have to teach next Friday. The semester is starting, so well, I'll figure it out. I am in it to win it. I'm in it to lose it. You have my random number video and blah, blah, blah. All right. Thank you, everybody, for being with me today. Send me your feedback in the comments when this live stream gets archived at Schiffman at Twitter. The live stream will be archived within an hour. I just leave it unlisted till Mathieu helps me has a chance to put in the description and the links to all the things. So yeah, I'm in it to learn it. So I will come back later. I'll be back next time. Definitely next Friday, if not. And next Friday will be a late one because I have a makeup class that I'm teaching here at NYU that goes until 3 o'clock in the afternoon about. So I'm probably going to be doing a 4 p.m. or 5 p.m. Eastern time live stream, which is very late, I know, for all of you international, depending on where you are, obviously, but international viewers. All right. Thank you, Socrates, Utna, Bruna, Gino, Zach, and Kay Weekman. I like to say your name with emphasis. Thank you. In it to win it. Hashtag in it to win it. Wilderness Dan. This will be longer. Wilderness Dan will be back. All right. All right. It's so hard to know, right? The thing is, should I just write this formula up on the board and implement the code and be go watch those other videos that explain it more? Should I explain it? I'm kind of being in the middle here, which I think is a bad place to be. The best place to be, I think, is I'm really going to explain everything and it's going to make sense, or I'm going to just present to you these formulas that I'm going to implement, and here are resources for you to dive deeper into those formulas. I'm kind of in the middle, so I'll come back and sort of sort that out. All right, this live stream is ending in 3, 2, 1. Goodbye and good luck. Have a wonderful weekend. Give a friend a hug, all that sort of stuff. Goodbye. Mwah.